Hi, in this video we will learn what is Gauss-Jordan elimination method to solve a system of linear equations. We already know all the steps, but the last step, let me list the steps to do the Gauss-Jordan elimination method, and then I'll explain the last step, which is a key step in this method. Okay, so when you have a system of linear equations, given, so the first step what we did, or what you need to do, is find the augmented matrix of the system. Augmented matrix of the system of linear equations. Step 2, use the elementary row operations, to transform the augmented matrix to the row reduced echelon form. So this is something we have learned. Now the last step is that while we have row reduced echelon form, we have to get the solutions of the system out of these cases. So for this, there are 3 cases. So determine which one of the following cases happen, and use it to find the solutions. Okay, what are these cases? Case 1. What is that? It is no solution case. So no solution. How does this can be seen from the row reduced echelon form? If we have a row, if row reduced echelon form has a row with all zeros, on the coefficient part, and a non-zero entry after the separating line. So this is like you have 0, 0, and goes up to, let's say this is the matrix, and then here this is the separating line. Here there is a non-zero, anything but 0. Okay, if that's the case, then system has no solution. If you row reduced echelon form has that kind of 0 on the left, non-zero on the right, there's no solution. That's case 1. Case 2, this is a unique solution case. What is unique solution? How does that come along? Well, if every column of the coefficient part of the row reduced echelon form. So every column has a has a leading one, contains a leading one. Has a leading one of some rows. So every column to the left of the separating line has a leading one in it. In that case, we have unique solution. How do we find unique solution? So to find it, to find the solution, now there's only one. So we have an augmented matrix, yes? Turn it back to the equation form. So turn back the augmented matrix to the equation form. Well, that will give you the solution. So that will give you the components of the unique solution. So that's case 2. If every column has a leading one, the system has a unique solution, then return back everything in the equation form, and that will give you, well, all the components. That's case 2. The case 3, remember how many solutions a system can have? No, only one or infinitely many solutions. So this is when parameters comes in. So you have infinitely many solutions. To describe infinitely many solutions, we will need parameters. So when does this happen? Well, there are some columns which are not containing any leading one. Case 1 doesn't happen, and then we have some rows, some columns has no leading one. What do we do, and how do we get the system, the solution, the infinitely many solution? Well, first of all, each column is for a variable, yes? So the columns, let me stop, whoops. Assign parameters to the columns without leading one. So the number of parameters that we are going to use is equal to number of columns without leading one. So, okay, so this says just how many parameters we have, but how we find the solution. So to each variable corresponding one of the columns without the leading one, assign the parameter we chose for that column. So assign the corresponding parameter. Those are the parameters. Then write down again, write back the equation form. Write back the equation form. And rewrite all the components or all the variables in terms of the parameters. It is a little bit long, but you will see it will come very naturally. For now, just remember that these three cases, no solution when we have 0, non-zero, 0 in the left, a row, 0 entries on the left, and non-zero entry on the right. Unique solution, every column has one leading one, and infinitely many solutions when there are columns without leading one. By the way, all case 2 and case 3 we are discussing here, we already checked case 1. There is no row 0 equal to non-zero. Okay, so let's just, before finishing this whole thing, let us do some examples for each case and see how this goes. These are actually examples that find the solutions, if there is anyone here. So these are the cases actually we already did the row reduction for. So one is this one, 1 0 0 0 1 0 negative half 3 negative half 0 0 1. Okay, the second one is yeah, 1 negative 3 0 negative 2 1/3 1/6 0 0 1 negative 1. And the last one is the one that we had here. It is 0 1 0 0 0 2. Okay, let's go one by one for these ones. First thing to check, is there any row 0 row equal to non-zero? No, all the rows are non-zero, so case 1 doesn't happen. That you should check first. Now, to check if it is unique or infinitely many, you check every single column if they have leading one or not. Does column 1 have a leading one? Yes, these are the leading ones. And you see that the column 1, column 2, column 3 have all a unique, a leading one. So this means that we have unique solution here. How do we solve this system? Well, what is that unique solution? Turn back this augmented matrix in the equation form. How do we do this? Well, let's say this guy is for x, this is for y, this is for z. Then we have 1 times x plus 0 times y plus 0 times z equals to negative half. Y is equal to 3 and z is equal to negative half. Well, we have all three components. The solution is negative half, 3, and negative half. For this one, first thing to check, is there any 0 row non-zero on the right hand side? No. Then check the leading ones. The column 1 has leading 1, column 3 has leading 1. We have 2 columns without leading 1, so that means we have infinitely many solutions. Infinite many solutions. Then what we do? Well, okay, so let's say this guy is x1, this guy is x2, x3, and x4. The rows without, the columns without leading one. Which one are these ones? X2 and x3. I assign t for this, t for that. Then what do I have? We have x1, x2 is equal to t. Oh, I have to assign different variables, s and t. Oops. So I assign s here, t there. Doesn't matter which one you choose. S and t. So x2 is ts. Oh. And x4 is t. Now, write back the equation form of the augmented matrix. This is x1 minus 3x2 minus 2x4 equals to 1 over 3. And the second one is x3 minus x4 equals to 1 over 6. We have 4 things. Write everything in terms of s and t. So x1 is going to be 1/3 of plus 3 times x2. x2 is s plus 2 times x4. x4 is t. That's x1. How about x2? x2, well, it's already there. It's just s. How about x3? x3 is, okay, right? Everything in terms of the parameters. 1 over 6 plus x4. x4 is t, so just right there. And x4 itself is t. Now we have the solutions for this one. The first component is 1/3 plus 3s plus 2t. The second component is s. Third component is 1/6 plus t. And the last one is just t. For different values of s and t, this will give us different solutions. And that's why you have infinitely many, because you can put infinitely many values for t and s. Very nice. The last one, you check. The first thing you check, is there any zero row equal to non-zero? Yes, there is here 0. This is non-zero. That means that we have no solution for this system. 3 cases: no solutions, unique solution, and infinitely many solution. No solution happens when the row reduced echelon form has a row 0 on the right hand side, non-zero. Unique solution happens when we have every single column has a leading one, and that 0 equal to non-zero doesn't happen. And infinitely many happens when you have some rows without leading one. Unique, infinitely many, no solutions.